There's a number of different reasons one might give for why our hypothesis is wrong. I'll leave the answers. There's probably a lot we'll come up with in class, but to me, my answers I came up with, first and foremost, is that our cost model doesn't represent everything that's happening. It doesn't capture, for example, the creation of the cumulative sum array. It doesn't capture the fact that in merge sort, we need to create another array that we copy stuff back and forth to, who knows whatever else. So if you wanted to do a really deep analysis to get the exact runtime comparison between the two, there's more happening than just character accesses. I think that character accesses will predict the appropriate and correct runtime in terms of order of growth, but in terms of getting the exact ratio of one algorithm's runtime versus another, doesn't seem to be the right thing. Now, I do want to note that there's one particularly thorny issue, and this is the out-of-nowhere thing I wanted to bring up in this particular video, is there's something known as the just-in-time compiler that is going to make these types of analyses, I guess, next to impossible. So what the heck is the just-in-time compiler, and how does that affect us? Okay, let's learn about it. It's pretty important stuff. I think it's very cool. So it turns out that Java, it has something known as the just-in-time compiler that is always optimizing your code as it is running. So you may remember this diagram from before. We have hello.java, which is compiled into a class file before execution. This does all the type checking and so forth. We then pass it to the interpreter, and then things happen. Now, this interpreter is far more complex than the interpreter that you built if you took 61A or 47A. In particular, one very cool feature it has is that it is constantly watching what your code is doing. It is profiling your code, saying, oh, it's doing this in this case and that in that case. And if it finds that some piece of code is used many times, it will actually re-implement that piece of code based on what it observed. So as an example, your code is running and it decides, oh, you keep computing some value that nobody actually uses. So I'm going to try and optimize, maybe not even compute that value at all. So while your code is running, the interpreter is studying and re-implementing the code on the fly. And if you're curious about the details, here's an 1.5 hour long video where a guy steps through tricks that he is a just-in-time compiler author, and he steps through some of the tricks used in order to create such a piece of software. It's pretty amazing stuff. Let's see an example just to make sure that this all makes sense. Here's a piece of code that is, I'm calling it JIT demo. It's provided in the lecture code repo. What this code does is pretty simple. I'll talk through it relatively slowly. So it does the following 500 times. It gets the current time. It creates 1,000 linked lists. It gets the time after those 1,000 linked lists are created, and then it prints out how much time was needed. So in other words, this block of code creates 1,000 linked lists and prints the total time it takes to create those 1,000 linked lists. And it does that 500 times. I've provided this code in the lecture code repo, and we can try running it and see what happens. So if we run JIT demo, something very surprising occurs. If I go to the very top, I see that the very first 1,000 linked lists that get created take 770,000 nanoseconds. That's almost a millisecond. Then 49,000 for the next 1,000 linked lists, and so forth. And we keep going, and then eventually something pretty interesting happens. We see that the runtime for each linked list kind of falls off a cliff at some point, around number 70 or so. It starts taking around 30,000 nanoseconds to create each linked list, which is better than what we saw before, which is in the 50K range. And it kind of bumps around between 20 and 30 for a while, but then at operation number 166, it starts speeding up a lot. And eventually, each 1,000 linked lists take only 300 or 600 nanoseconds. That is, this piece of code is getting faster and faster as the piece of code runs. So here, we can actually plot the runtime for each of those linked list creations. We see at the very beginning, we have a very slow first linked list to create. This is a warm-up period while the interpreter is just getting going. Runs for a while, and then there's a first set of optimizations that's done somewhere. I don't know what they are. And then once we get up to this point, somewhere later, this is a different set of data than what I just showed, but at some point we fall off a cliff in terms of the amount of time needed per linked list creation. And here it starts taking almost no time to create the 1,000 linked lists. This is our second optimization. And in this case, if you watch the video by the just-in-time compiler author, he states that what it does is it stops creating linked lists because it realizes that we're not actually using them at all. That's pretty cool. Okay. So here, The point is that there is this whole secret world happening when your code's running about that you don't even know about that makes these kind of analyses very tricky. So I think it's an interesting experiment. Let's try, in the next video, I guess, because this one's getting perhaps a little long, let's try running our computational experiment on our sorts again, but with the just-in-time compiler disabled.